So we were on section 2.5, the chain rule, and we left off with, what number did we leave off at? Yeah, this one. So we're at 250. So 250. So for the following exercises, use this information. A function fxy is said to be homogeneous of degree n if, well, let's leave out 250. That's a little bit too esoteric for now, I think. So section 4.5, so number 250, omit that one. So number 254 is the next one. So the volume of the frustum of a cone, so it's a cone with the top lopped off of it like that, and is given by this formula here, where x is the top radius, y is the bottom radius, and z is the height. Find the rate of change of volume when x is equal to 10 inches, y is equal to 12 inches, z is equal to 18 inches. They don't say. They're missing some information here. Another one of these typos in the book. Mark this on the syllabus. I got to talk to the coordinator of the class, tell them that we need to fix these things. It's 254. All right, so what they should tell you is, how these things are changing. So this is a related rates problem. So the volume, and it doesn't even matter what it is, the volume of this thing, doesn't matter what the thing is pi over 3 times z, x squared plus xy plus y squared. Okay. So now they don't say this in the problem. So in the problem, x, y, and z vary with respect to a time parameter t. So x, y, and z are functions of t, which makes v, volume, a function of t. V is a function of x, y, and z, okay, but since x, y, and z are all functions of t, v is actually ultimately a function of t. Now, they don't say in the problem what dx dt dy dt and dz dt are. Okay, so like just for the sake of argument, let's say that, for example, that dx dt is equal to dy dt is equal to half an inch a minute. So x and y are increasing at half an inch a minute, and dh dt is equal to negative 1/10 of an inch per minute. So it's decreasing at 1/10 of an inch per minute. The z, or not h, the z. All right, so the height of that object, that cone frustum. Okay. So now they ask you find dv dt. Suppose e. Oh no, they do say. Oh, here it is. Suppose each dimension is changing at half an inch a minute. Got it. Okay. It does say. I didn't read it carefully enough. So they tell us that these are all increasing 0.5 inches per minute. And now they're asking you, so they're all increasing at half an inch a minute. So now what is dV dt? What is the range of change of volume when x, y, z is equal to 10, 12, and 18 inches? Okay, so what is the rate of change of volume given the rate of change of big radius, small radius, and height? Okay, well, before in single variable calculus, you had to use implicit differentiation. So here we just use the chain rule, right? So v is a function of x, y, and z. And x, y, and z are functions with respect to t. So the chain rule states that dv dt is equal to, well, partial v partial x dx dt plus partial v partial y dy dt plus partial v partial z dz dt, right? So you can figure out these partial derivatives, dx dt, dy dt, and dz dt are all this constant here, half an inch a minute, and then you're wondering about the point in time when x, y, and z is 10, 12, and 18. Okay, so we just have to fill in the blanks here, right? So dz dt is what? Or dv dz, partial derivative of v with respect to z. That's the easy one. What is it? Well, they're all easy. But... right, so z is the variable, and x and y are constants. So everything's a constant except for that z. So partial derivative of v with respect to z is...
everything else besides z.
Yeah, just that whole function again with the z gone. X squared plus xy plus y squared. Partial v partial x is equal to, well, so now the pi over 3z is just a constant, and we just take the partial derivative on the inside. So that's 2x plus y plus 0. And partial v partial y, same thing. And that's 2y plus, or 2y plus x. Right, 2y for that plus x for that one. So now we're interested in the instant in time where x, y, z is 10, 12, 18. So dv dz at 10, 12, 18 is equal to, well, I mean, it's some big thing here. So pi over 3, 100 plus 120 plus, what's 18 squared? Where's my phone? 18 squared, so 324. So 324 plus 100 plus 120, 544 divided by 3, so 181.33. And then I'll multiply by pi as well, times 3.14159. So 596.67. And then dv dx at 10, 12, 18 is pi over 3 times, oh, what did I do? 10, 12, I put an 18 there. No, this is 144. So that's 364 divided by 3 times 3.14. So 380. I'll just round off to the nearest whole number. So this one is pi over 3, z, which is 18, times 2x, which is 200, or no, which is 20, plus y. Y was 12. So 32 times 18. And 32 plus, yeah, 32 times 18 divided by 3 times 3.14. So 603. And dv dy at 10, 12, 18 is pi over 3 times 18, 2y, which is 24, plus x. So 34 times 6 times pi. So 640. Okay, so now we just plug in all those numbers. So dv, or regular derivative, dv dt is equal to, well, at 10, 12, 18. So dv dt at 10, 12, 18, at some other point in time, at some other parameters for x, y, and z, it'll be different, is equal to dv dx, 381, times 0.5, plus the 603, doesn't matter, but all the same, times 0.5, 640, times 0.5, plus 381 times 0.5. So 640 plus 603 plus 381 is all that divided by 2. So 812 inches cubed per minute. All right, so the rate of change of volume is 812. Right, so the multivariable calculus, it just makes these related rates problems just a simple application of the chain rule. Then you got to plug and chug a bunch of numbers. Hopefully I wouldn't give you a problem that sort of nasty on the exam, but we'll definitely have one of these on the exam. Let's see what else we got in this section as far as those related rates problems go. So on the syllabus, there is 254, then there's 255. All right, this one's a little bit different, a little bit simpler. So a closed box is in the shape of a rectangular solid with dimensions x, y, and z in inches. Suppose each dimension is changing at half an inch a minute. Okay, they're going the boring route again. They're not making them different. So anyway, you have dx, dy, and dz, dt. They're all 0.5. Find the rate of change of surface area when the box is 2 by 3 by 1 inches in 255. So 255, you've got this rectangular box. All right, we'll call this dimension x, the width, this dimension y, the depth, and this dimension z, the height. Okay, so, and they're saying to us that dx dt equals dy dt is equal to dz dt, again, is 0.5 inches per minute. Of course, they don't have to be equal, but, I don't know why they're doing it that way, but that's what we got there. Find the rate of change of surface area with respect to time when x, y, z is equal to 2, 3, and 1. 2, 3, 1. Okay? So, first of all, the surface area A is equal to the surface area. And what's that surface area of this thing going to be? Well, it's the area of each of the rectangular faces. Right? So the front face, what's the area of this front face here? What's the area of that?
XZ, but there's two of them.
Yeah, do add x times z, but there's two of them. Alright, so 2xz plus, and then you have 2yz for the right and left face, and then for the top and bottom face, 2xy. Right, so again, you've got the area as a function of, or whatever the measurement is a function of x, y, and z, and x, y, and z are both functions of t. Right, so dA dt in general is equal to partial A partial x dx dt plus partial A partial y dy dt plus partial A partial z dz dt. All right, so dA dt is equal to, so, well, let's find those partial derivatives here. So partial derivative of a with respect to x, and this is a completely symmetric function in x, y, and z. So partial derivative of a with respect to x is z plus y, 2z plus 2y. Right? X is the variable, z and y are constants. So that's a constant that goes away. This one is just give you 2z, this one just give you 2y. So dA dx is 2z plus y, partial a partial y is 2x plus z. So let's call this y plus z. Do them in alphabetical order. And partial a partial z is 2x plus y. Right, so at 2, 3, 1, so partial a partial x at 2, 3, 1, so is 8. Partial a partial y at 2, 3, 1 is equal to 2 plus 1 is 3 times 2 is 6. And partial a partial z at 2, 3, 1, 2 plus 3 is 5 times 2 is 10. So dA dt is equal to dA partial a partial x, which is 8, times dx dt, which is 0.5, which is the given information. dA dt is, I guess I should put 2, 3, 1. Partial a with respect to y is 6 and times dy dt, which is 0.5. And partial a partial z is 2 times x plus y, which is 10, times dz dt, which is 0.5. So we get 4 plus 3 plus 5 is equal to 12 inches squared a minute. Right, so the rate of change of surface area is increasing at 12 inches squared a minute. Now, in these problems, I don't know why they're always giving us the same for all the different parameters, that the rates of change are the same. I mean, they could mix it up, they're just not. Right? No implicit differentiation, just plain old chain rule. Um, 257. So the temperature at a point xy is txy and is measured using Celsius scale. A fly crawls so that its position after t seconds is given by x equals 1 plus t square root 2 plus 1/3 t, where x and y are measured in centimeters. The temperature function, partial derivative of t with respect to x, is 4 at 2, 3. And partial derivative of t with respect to y at 2, 3 is 3. How fast is the temperature increasing on the fly's path after 3 seconds? So they do not give you the temperature function. But we don't need it because they gave you the partial derivatives already. What is the significance of the 3 seconds, by the way? What is the significance of the t equal to 3 seconds? Where is the fly, x and y, at t equal to 3 seconds?
At x equals 2?
Yeah, x equals 2, y equals 3. Right? So in 257, so you've got some xy plane, and you've got your ant crawling around that xy plane. Right? And at t equal to 3 seconds, right, x is equal to 2, y is equal to 3, where x, his position, is 1 plus t square root, right? So at t equal to 3 seconds, he's at x equal to 2, because that'll be square root of 4. And this is 3 plus, or 2 plus 1/3 t. So at 3 seconds, this is at 2 plus 1 equals y coordinate 3. So this is the point x, y equals 2, 3 at 3 seconds. All right, and then they're telling us that partial t partial x is equal to 4. And partial derivative of t with respect to y is 3. Find dt dx, or d capital T, d lowercase t. So again, little t is time, and this is temperature. That's unfortunate. They use t both times. So find d capital T over d little t. So the rate of change of temperature with respect to time. Okay, so the chain rule states that, so again, you have a temperature function t is a function of x and y are both functions of t, which are explicitly given right there. Right, and we're going to use that for sure. Okay, so the chain rule states that the derivative of temperature with respect to time is partial of temperature with respect to x times dx dt, plus the partial of temperature with respect to y dy dt. Right, so the rate of change of temperature with respect to time at t equal to 3 seconds is, well, dt dx, partial t with respect to x, at 3 seconds, which was 4. And then this is dx dt. Plus, well, actually, let me calculate those in a minute. Plus partial of t with respect to y at 3 seconds, and that one was 3, times dy dt. But we'll find those right now. So dx dt is equal to what? So it's 1 plus t to the 1/2, the function. So this is 1 plus t, so 1/2, 1 plus t to the negative 1/2. So dx dt at t equal to 3 seconds is 4, so 1/4, so 1/8. And dy dt is just 1/3. So these numbers are 1/8 and 1/3. So dx dt 1/8, dy dt 1/3. So this is 1/2 plus 1, so that's 3/2 degrees Celsius. Degrees Celsius per minute. Was it minute? Minutes? Seconds. So, that's an odd numbered problem, so you can give that a quick check in the back of the book, 257. Two degrees Celsius per second. Whoops, 3/2. Where'd they get 2? 2 degrees Celsius per second. So at t equal to 3, so that's 4. Square root of 4 is 1/2. This is 1/4. Yeah, that's square. This is square root of 4. Well, 4 to the negative 1/2. So 1 over the square root of 4. So that's 1/2. So 1/2 times 1/2 is 1/4. So that's 1 plus 1, which is 2 degrees Celsius per second. Okay. So those are nice. How related rates really is done really properly using the chain rule. So we'll have one chain rule type problem on the exam on Monday. Sorry, one related rates. On the exam on Wednesday. Using the chain rule. Okay. Alrighty. Before we move on to 4.6, let us take our break today, 5-minute break, a little early. So it is 7:04. So let's come back at 7:10. Okay, so we'll take 5 minutes and come back then. Okay. All right. So one of these related rates problems for the exam, like I was saying. So, go over these examples that we just did, and it'll be a sufficient preparation for that. All right, section 4.6 on the directional derivative and gradient. So starting with number 262. Alright, so find the directional derivative for this function, fxy, y squared sine 2x at the point pi over 4 comma 2 in the direction of 5I plus 12j. Okay, so 262, right? We've got fxy equal to y squared sine 2x, right? And find the directional derivative in the direction of u for f at pi over 4 comma 2. Right, so first we find the gradient vector. So the partial derivative with respect to x, right, the y squared is just a constant, so it's 2y squared cosine 2x. And the partial derivative with respect to y is 2y sine 2x. Right, the derivative of y squared is 2y and the sine 2x is a constant. So the gradient of f in terms of just x and y is equal to, well, it's the vector of these partial derivatives. Okay, but of course we are interested in the point pi over 4 comma 2. So the gradient of f at pi over 4 comma 2 is equal to, so this is 4 times 2 is 8, so 8, and then that's root 2 over 2. And this one is 2 times 2 is 4, root 2 over 2. So the gradient of f, at that point, pi over 4 comma 2, is 4 root 2, 2 root 2. Right? The direction, right, for the directional derivative is that of the vector 5, 12, 5i plus 12j, right? Now, the length, how do we get, but we need a unit vector, right? We don't want the direction vector to be anything other than a unit vector. So, of course, the length of this, 512, that's 25 plus 144, square root, which is 169, square root, which is 13. That's one of the Pythagorean triples, 5, 12, 13. So, the unit vector for the direction is v over the length of v. So that's 1/13 of this. So that's 5/13, 12/13, right? So that's a unit vector pointing in the same direction as 512. So the directional derivative of f at pi over 4 comma 2, that is just the gradient of f dot u. Right? Real, I mean, the ingredients take a little bit of calculating, but I mean, it's just the dot product. this gradient f dot u. So 4 root 2 comma 4 root 2 dot 5/13, 12/13. So this becomes what? 20 root 2 over 13, there's a 2 root 2 here. 20 root 2 over 13 plus 24 root 2 over 13. So that is 44 root 2 over 13. Huh. Okay. All right, 265, more the same. So we have the three-dimensional, the three-variable function h, and you have the point p11, you have the direction vector 2, 1, -1. Find the directional derivative in that direction. So for a three-variable function, four-variable function, what have you, right, the gradient, the directional derivative is, again, just the gradient dot the unit vector. It's always that in any dimension. So in 265, right, h is x, y, z. So h of x, y, z is just x times y times z. Right, so hx is yz, hy is xz, hz is xy. And the point we're looking at is 211. So hx at 21, well, so the gradient of h is equal to yz xz xy. So the gradient of h at 211, right? So that's the gradient of h for x, y, z. In this case is, so the x is 2 and the rest are 1, so that's 1, 2, 2. 1, 2, 2. Right, and the direction vector v is given to you as 2, 1, -1. 2, 1, -1. Of course, that is not a unit vector, so the length of v is 4 plus 1 plus 1, square root 6. So the unit vector for the direction of the directional derivative is v over its own length, and this vector now has length 1, so this is 2 over root 6, 1 over root 6 minus 1 over root 6. Okay, and so the directional derivative for u, in the direction of u of h at what was the point? 211 is again just equal to the gradient of h dot u. So this is 1, 2, 2 dot 2 over root 6, 1 over root 6 minus 1 over root 6. So that's 2 plus 2 minus 2. So that's just 2 over root 6. Right, and of course the directional derivative is a number. Right, it's a slope. What is that slope? I mean, this is for a two-variable function. This is for a three-variable function. It's a little bit sort of difficult to describe geometrically. But geometrically, what is the directional derivative? Well, what is the partial derivative with respect to x? What does that represent geometrically? Since we're talking,
Would it be a point?
Right, so you have the tangent plane, right? And the tangent plane's got some kind of slant to it, right? The slant, so if you take the line in the tangent plane in the direction of the x-axis, that's the directional derivative for the vector 1, 0. And it's also the partial derivative with respect to x. So let's find the picture. It's nice to think about these calculations that you're doing here. There it is. Right, so the slope of this, so that's your surface right there, that black thing that I drew. And then if you take the tangent plane at this point, right, and you take the slope of the line in the tangent plane, that is in the direction of the x-axis, like in the direction of the x-axis, it means if you project it down into the plane, if you shine a light from up top and project it straight down, then that shadow that you get in the, I can't draw on this, but that, if you can see my cursor, that shadow of the orange line, the orange shadow, not that the shadow is the same color as the line, but the shadow of the orange line parallel to the x-axis when you shine the light down, okay, that slope here, okay, in that direction of the x-axis, that's the partial derivative with respect to x, but it's the directional derivative for direction 1, 0. The green slope, that's the directional derivative for the direction 0, 1. That's in the direction of the y-axis. Oops. But hey, why restrict your attention to the x-axis and the y-axis? You can go, so if you take that point and take an arrow coming off that point, right, so you've got your surface. And you've got this point of tangency up here. Right, you can turn that sort of disk in the tangent plane of vectors. So you have that tangent plane, you take this little disk around it, and you could spin that vector around, right? And the slopes in all those different directions, those are the directional derivatives. And the cool thing about the directional derivative, right, is that the directional derivative in this direction and in the 180 degrees direction, right, they are negatives of each other. Like this slope would be 2 and this slope would be negative 2. And the greatest slope is the direction of the gradient itself. Right? So that's the popular usage of the term gradient. But that comes exactly from here, from Calc 3, is that the direction of greatest increase is the direction of the gradient. Or, you know, I mean, if you want to do it the other way, the direction of greatest decrease, that's the negative of the gradient. You can call that the gradient. All right, so, you know, that's an important concept in physics, this gradient and direction of the gradient. I mean, you know, the standard example people always think of is if you have a surface that's essentially the top of a hill or something like that, and you pour water onto the ground, which way is it going to flow? It's going to flow the fastest way down, which is the direction of the gradient. So the path that water follows downhill basically goes with the gradient vector at each point. So it's a cool idea, the directional derivative, and it has some neat meaning and some interesting geometry and interesting calculus. All right, so what else we got? That was 265. 2 272, 275, 278, more of the same. 272, 275, 278. $284. I mean, this is all just more of the same here. Let's 272, 275, 278. You can do those on your own. I do on your own. 284. Let's do that one. It's interesting the way they stated the problem. So you've got the following function, fxy. Find the directional derivative at the point P in the direction of Q. So what do they mean by that? So fxy is equal to x squared plus 3y squared. And in the xy plane, you have point P being 1, 1. And Q being 4, 5. So over here or something. All right, so find the directional derivative at P in the direction of Q. So that's the vector that you're looking at. All right, so the vector V here is 4 minus 1 is 3, 5 minus 1 is 4. So the length of V is 5. So the unit vector for the direction is V over the length of V. So that's 3/5, 4/5. Like that. Right, so they're asking you for the directional derivative in that direction. And the unit vector for it is, is right there. That one has got length a lot more than 1. The unit vector has length 1/5 of that. So that's the unit vector u right there. All right, so partial derivatives, find the gradient now. Partial derivative with respect to x is 2x. Partial derivative with respect to y, 6y. So the gradient of f at xy is 2x, 6y. So the gradient of f, now we're finding the directional derivative at 1, 1. So this is 2, 6. Right, so the directional derivative in the direction of u of f at 1, 1, where u points to from P to Q, is gradient f dot u. So that is equal to 6 dot 3, 5, 4, 5. So 6 plus 24. So 30 over 5 is 6. So the slope is 6 for the function in that direction. Now, where is the problem asking about the largest value of the directional derivative? So 287, 291. So 287, more of the same. Do on your own. 291, 294. Same. Or 291. 294. For the following exercise, find the derivative of the function fx at the point -4 in the direction that the function increases most rapidly. Okay, so for 294, we have fxy equals x squared plus xy plus y squared. So find the largest directional derivative at xy equal to minus 5 minus 4. Right, so the partial derivatives are, in this case, 2x plus y, and fy is 2y plus x. So the gradient vector for xy is 2x plus y, 2y plus x. So the gradient vector at minus 5 minus 4 is equal to so x is minus 5, minus 10, minus 4, minus 14, and minus 8, minus 5, minus 10, minus 4 is minus 14. And this is minus 8, minus 5, all right, negative 13. Okay, so the gradient vector, the largest directional derivative is the gradient vector itself, right? I mean the length of the gradient vector. Since the directional derivative in the direction of u of f is equal to the gradient of f dot u, which is equal to, well, what's the dot product? It's the length of the gradient times the length of u times the sine, or times the cosine of theta. But the length of u is 1. Right? So it's the gradient of f, the length of the gradient of f, times cosine theta. But cosine theta is a maximum at 0. At theta equal to 0. So, gradient of f is the largest, length of the gradient of f is the largest directional derivative. So in this case, the gradient of f at minus 5 minus 4 is equal to the length of minus 14 minus 13, which is equal to square root of 14 squared plus 13 squared. Where's my phone? So 19.10. So that is the largest directional derivative. What is the smallest directional derivative? Smallest in terms of negative numbers, the largest negative number. So the smallest would be the largest negative number, right? So I mean, like, This directional derivative is, in this direction, is 19.10. In the opposite direction, it's negative 19.10. What happens when it's perpendicular? What's the directional derivative in the perpendicular direction to the gradient? Well, perpendicular means theta is 90, right? Gradient f dot u, where u is, 90 degrees from the gradient. So that gives you a directional derivative of what? Since they're perpendicular, these two vectors. What's the sine of, or no, sine, what's the cosine of 90? Right, 0. So this is the length of the gradient. This is the negative of the length of the gradient. And these are 0, which is 90 degrees from the gradient. So the geometry of the slant of that tangent plane is it's got some interesting bits to it. So next, that was 294. 296, same thing, right? Arc tangent y over x is your function. So at the point negative 9, 9, find the directional derivative that's in the direction the function increases most rapidly. Again, it's just the length of the gradient. So arctan y over x, let's give that one a go. So find max directional derivative at negative 9, 9 or 9, negative 9? Negative 9, 9. Right, so the partial derivative of f with respect to x is, well, derivative of the outer function, 1 over 1 plus y over x squared times the derivative of the inner function, negative y over x squared. Partial derivative, so let's simplify this expression. What do we have here? So this is 1 over 1 plus y squared over x squared times x squared over y, putting that fraction underneath. So that becomes 1 over, well, that's not any nicer looking than if we just put the y on the top. So this is minus y over, multiply through by x squared here, x squared plus y squared. All right, so that's the partial derivative with respect to x. It looks like the preferred way to write it. Partial derivative of f with respect to y, 1 over 1 plus y over x squared times the derivative of the inside. In this case, it's just 1 over x because that's the constant times y. So we get 1 over x plus y squared over x. And you can add these two fractions together. So that's x over x squared plus y squared. And I am really surprised that that came out so similar to the other one. That is shocking. So 1 over that square, and then minus y over x squared, because y is the constant. Put the minus y on the top through x squared on the bottom, you get that. This one, it's times 1 over x. So just multiply through on the bottom by x, y squared over x, which is x squared over x plus y squared over x. It's x squared plus y. Yeah, that's right. That is right. So the gradient for xy is equal to minus y over x squared plus y squared, comma x over x squared plus y squared. What do you notice about that, by the way? The length of the gradient. So I don't even have to plug in the -9 and the 9. What's the length of that gradient? Oh, no, sorry. Not true. You do have to plug in it now. See? That was hasty. So -9, 9. So x equals -9, so that's 9 over 81, 162. And then 9, or no, I'm sorry, I did that wrong. -9, that's the y. This is -9 as well, over 162. So the max directional derivative is equal to the length of the gradient of f at -9, 9, which is equal to, that's 9 root 2 over 162. Yeah. Okay. Yeah, so 162 must divide evenly by 9. 18. So that is root 2 over 18. All right. So that was 296. $300, 302, 306. So 300. I'm sorry, guys. I have to get up just for a second. I'll be right back. Okay. 300. So for the following exercise, again, the same thing. For the following exercises, find the maximum rate of change of f at the given point and the direction in which it occurs. So give me the direction. The direction is the direction of the gradient, essentially. So fxy is x squared plus 2y square root So fx is, so this is 1/2 x squared plus 2y to the negative 1/2 times 2x. So those cancel, and you've got x over square root x squared plus 2y. Fy, gonna get something similar. It's just going to be 1 over square root x squared plus 2y, because you're still going to get this expression, but the partial derivative of the inside is just 2. Okay, so the gradient of f at xy is x over square root, and then 1 over square root x squared plus 2y. So the gradient of f at the point that we're interested in is 410. So this is 4, and then square root of 108. Right, x squared is, or no, wait, x squared is 16. Plus 2y is 20, it's 36. So 4 over 6, and then just 1 over 6. Okay, so that's the gradient. The largest, so the max rate of change is just the length of the gradient at 410, which is 16 plus 1 is square root 17 over 6. Right, in the direction u equal to, well, it's given by the gradient of f itself. Gradient of f over the length of the gradient of f. So that is 4 over root 17, comma 1 over root 17. So that's the unit vector pointing in the same direction as the gradient itself. And then the least rate of change is, well, sorry, not, the least in terms of the number line, furthest to the left along the number line, is negative root 17 over 6 in the direction of negative 4, negative 1 over root 17. All right, 302. For the following exercises, so this is a little bit, some more stuff about the gradient and with the level curves. For the following exercises, find the equations of the tangent plane and the normal line to the given surface at the given point. So something to remember. Okay, so before we do 302, remember this. So for a two-variable function, right, f, x, y, the gradient vector gradient f at any point, a, b, is perpendicular to the level curve. level curve fxy equal to fab. Fab is going to be a constant at the point AB, right? Because if you've got the level curve, so this is f of xy equal to fab, which is some constant k. So now if you take the point on that level curve, AB, right, the slope here is dy dx. The slope of the tangent line is dy dx. But, we showed that this is equal to, right, via partial derivatives, so via the chain rule from the last section, we showed that this is the negative of the partial derivative with respect to x over the partial derivative of f with respect to y. Right, and this, which is the slope, of the line with direction vector, right? So that's the rise over the run, right? This is the rise over the run. So the rise is minus fx. Sorry, that's the change in x. Sorry. The rise is on the top. That's the change in y. So that's the minus fx. And the change in x, the run, that's the denominator, fy. But this vector fy, comma, minus fx, fy, comma, minus fx dot fx, comma, fy is 0, right? So the gradient of f, which is this, is perpendicular to the tangent line. Right? The tangent line has that slope, and it's perpendicular to this, which is the gradient. Right? So in this picture, the tangent line has slope dy dx, but we showed, in section, so this is by the chain rule. Partial derivative of f with respect to x over partial derivative of f with respect to y. And that's rise over run for this vector. All right, the run is negative fx, that's the numerator. The rise is the denominator. And that has dot product 0 with the gradient of f, which is fx, comma, fy. All right, so the gradient is perpendicular to the level curves. So if you look at the function of a two-variable function, if you look at not its graph in 3 dimensions, if you look at its level curves, which is, in lots of ways more interesting. Remember, a lot of times you might see like maps of, of various places in the world, and they'll have lines of elevation. They'll have curves labeled by elevation. It's 300 feet above sea level. Along this curve, it's 400 feet above sea level along this curve, so on and so forth. Those are the level curves for this mountain surface or whatnot. Right? And the gradient, which represents what? The gradient represents the direction of greatest increase. The direction of greatest increase, when you look at it on the level curves, so when you project it into the, two-dimensional xy plane, it's always perpendicular to the level curves. Boom. right? The calculus tells you that's the greatest rate of increase, but the geometry is telling you the exact same thing via perpendicularity. Or orthogonality, if you like that word better. The same holds true for three-dimensional functions and level surfaces. Although the reasoning is a little bit different. All right, that is the gradient of f at A, B, C is perpendicular to the level surface f of x, y, z equal to the constant f of A, B, C. So gradient, again, perpendicular to the level thing. So in 302, you have f of x, y, z is equal to 4x squared minus 2y squared plus z squared. Find the equation of the tangent plane to the level surface at 222. Uh, 4x squared minus 2y squared plus z squared equals f of 222, which is going to be, so 16 minus 8 is 8 plus 4 equals 12. So find the equation of the plane tangent to the level surface, 4x squared minus 2y squared plus z squared equals 12, at the point 222. Right, so you just calculate the gradient vector, and the gradient vector will be the normal vector, right? So what do we need for, a tangent plane? You need a point. Well, we got that. And you need the normal vector. Well, we get the normal vector. So this is a different method of finding the tangent plane for a surface defined with three variables. Okay, you push all the variables to one side. You pick a point that you're interested in on the surface, and then you look at that level surface and calculate the gradient. So different than the tangent plane equation z minus fa. So this is for a different function. Z minus g of ab equal to fx at a, not fx, gx. Partial of g with respect to x at ab, x minus a, plus partial derivative of g with respect to y at ab times y minus b. But what's the normal vector in this equation here, right? What is it? Right, the coefficient of x is partial derivative with respect to x. The coefficient of y is the partial derivative with respect to y. And the coefficient of z, when you move the z over here, is -1. But that's the partial derivative with respect to z if you'd have just plain old z. Right? So that's the gradient. Yeah? So it's all, different looks at the same thing, just getting more and more meaningful as you go along. right? So here the normal vector is just the gradient of f at 2, 2, 2. So fx is 8x, fy is minus 4y, fz is 2z. So gradient f x, y, z is 8x minus 4y and 2z. So gradient of f at 2, 2, 2 is 16 minus 8, 4. And that is the normal vector. All right, so the tangent plane n dot x, y, z is equal to n dot 2, 2, 2. So this is 16x minus 8y plus 4z is equal to, so the sum of these times 2, so it's 20, so it's 12 times 2, 24. So I think we can divide that by 4. So 4x minus 2y plus z equals 6. So there's your tangent plane. So, right, and the last, so what was weird was the book back in section 4.4, they were asking you about tangent planes, and they gave you a surface for which you couldn't solve for z. And they're saying to solve for z and now find the equation of the tangent plane at this point. But you can't. But now we can. Right? Now we can. So let's go back to that one problem to get revenge on it. So back to 172 from section 4.4. I mean, if you're of a mind that, doing math is like doing battle or something like that. I had a friend in grad school that was like that. It was funny. So, I think it was 172. Let me see. Tangent planes and linear approximations. Yeah, this is it right here. So for the following exercises, find the equation of the tangent plane of the surface at the indicated point. Hint, solve for z in terms of x and y. But you can't in 172 because you have a term with a z squared and a term with a z. You just can't do it. But now, we just call this, this surface here, defined by 3 variables, you just call it the level surface of a certain function, right? A certain function that equals 0 at the point -1, -1, -1. Because at -1, -1, -1, right, this is 1 plus 1 plus 8 minus 10 is equal to 0. So in 172, find the tangent plane to x squared plus 10xyz plus y squared plus 8z squared equals 0 at point -1, -1, -1. So, right, let w of x, y, no, let's not call it w, f of x, y, z be equal to this, x squared plus 10xyz plus y squared plus 8z squared, right? The point -1, -1, -1, -1, -1, -1, -1 is on the level surface f, x, y, z equal to, well, 0, which is f of -1, -1, -1. So the normal vector for the tangent plane is just the gradient. The tangent plane, pick normal vector equal to the gradient of f at -1, -1, -1. Right? So, I mean, it's no big deal. I mean, you can do it, but they gave you the problem before you knew, or how we discussed how to do it. So, I mean, I couldn't really, at that point when we were doing it, say to you, well, you just use the gradient, because we hadn't covered that yet. So, partial derivative of f with respect to x is 2x plus 10yz. Partial derivative of f with respect to x, or y, is 2y plus 10xz. And partial derivative of f with respect to z is 16z plus 10xy. So at 1, 1, 1, or -1, -1, -1, what do we get here? This is -2 plus 10 is 8, right? -2 plus +10. -2 plus +10 is 8. -16 plus +10 is -6. So the gradient of f, which is the normal vector, which is going to be the normal vector, is equal to 8, 8 minus 6. So the tangent plane is n dot x, y, z equals n dot -1, -1, -1, because that point of tangency is on the plane. That's the one point on the plane that we know. So we have 8x plus 8y minus 6z equals n dot -1, -1, -1. So that is -16 plus 6. So -10. So that's 4x plus 4y minus 3z is 5. All right, so there's the tangent plane. So we have these two equations for looking at the tangent plane. There is that very structured equation that we used in section 4.4 that has that special form like the tangent line, like a general. It contains both, tangent line in the x direction, tangent line in the y direction. And then you amalgamate those together into the tangent plane, right? But this one is different. It's a level surface technique, and we see now that the normal vector is the gradient, whereas in that other equation, it showed it to be the gradient anyway. The normal vector was fx, fy, -1, but when you have z equal to fxy, if you just move the z over here, fxy minus z, and then you call this a new function, h of xyz. Right, you call that a new function, h of xyz. Well, the gradient of h is the partial derivative of f with respect to x. Right, partial derivative of h with respect to x is f with respect to x minus 0. With respect to y is y with respect to x minus 0, or h with respect to y is f with respect to y minus 0. And partial derivative of h with respect to z is negative 1. So this is actually the gradient of h. Right? So same idea, just in a different form. There's another way of looking at the tangent plane using surfaces that are defined parametrically, but this book doesn't really cover that topic too well. The previous book we used did, although it will cover it later. It just does a shorter job with it. So that was the end of 4.6, I think. .302, and then there's 306. So the temperature T in a metal sphere is inversely proportional to the distance from the center of the sphere, the origin. And the temperature at point 122 is 120 degrees Celsius. Find the rate of change of temperature at point 122 and the direction toward point 213. Show that at any point in the sphere, the direction of greatest increase is given by the vector that points towards the origin. 306. It's an interesting looking problem. So you've got the sphere centered at the origin. Alright, so that's 0, 0, 0. And the sphere has it doesn't tell you what the radius is, but the temperature at any given point. So if you've got some point inside the sphere, not necessarily on the sphere, solid sphere. So that's point x, y, z. The temperature at x, y, z is inversely proportional to the distance from the center. Right, so that's the distance from the center of the sphere. So the temperature is inversely proportional to that distance, which is just x squared plus y squared plus z squared, right? Square root of x squared plus y squared plus z squared. It's just the length of that vector from 0, 0, 0 to x, y, z. So it's kind of like, you're heating the ball from the outside, or the sphere's dipped in some hot liquid or something like that, and it's hotter on the outer surface, and then as you go towards the center, it gets cooler, right? Because the heat needs to radiate inward from the outer part. And then they tell you that the temperature at 122 is 120 degrees centigrade. Find the rate of change of temperature as you go towards the point 213. So here's 122, and here's the point 213. So the vector in between these is 1, negative 1, 3 minus 2 is 1. So the unit vector for the direction is v over the length of v, which is just square root 3. So that's 1 over root 3 minus 1 over root 3, 1 over root 3. Yeah, so find the rate of change of temperature from point 122 towards point 213. So for part A, the rate of change of temperature is the directional derivative of temperature in the direction of u at point 122. So we calculate the gradient. So this is a nice symmetric function in terms of x, y, and z. So the partial derivative of t with respect to x. So this is x squared plus y squared plus z squared to the negative 1/2. So the derivative is negative 1/2 x squared plus y squared plus z squared to the negative 3/2 times k times the derivative of the inside, 2x. So the 2 and the negative 1/2 cancels. So this becomes kx over x squared plus y squared plus z squared to the 3/2. And so now the temperature, the derivative with respect to y, same thing. Just exchanging, because it's a nice symmetric function with x, y, and z. So you just get the corresponding partial derivative where y takes the place of x. And this one where z takes the place of x. Oop, not to the negative 3/2, to the positive 3/2. Right, so at the point 122, so what is this at 122? 4 plus 4 plus 1, so that's 9. So the gradient of f at 122, so this is 9 on the inside. Square root of 9 is 3, so over 27. So this is k over 27. 2k over 27. 2k over 27. Not 2z, but 27. So the directional derivative of t at 122, the rate of change of temperature, is u dot the gradient of f. Right, so this is 1 over root 3 minus 1 over root 3, 1 over root 3 dot, so 1 over 27, or k over 27, k over 27, 2k over 27, 2k over 27. So this becomes k minus 2k plus 2k. So that's k over 27 root 3. All right, so it's degrees Celsius per unit traveled or whatnot. Now, the rate of change of temperature is the greatest in the direction of the gradient itself. So in part B, the greatest rate of change of temperature at any point x, y, z is in the direction of the gradient of f at that point. But the gradient of f in terms of x, y, z is just k over this constant times the vector. Well, I'll write it out. So it's k over kx over x squared plus y squared plus z squared to the 3 halves. And then for the other ones, it's just y and z of that same expression. Right, but all of these are just the scalars times x, y, z. So it's k over this expression to the 3 halves power. So that's all just a scalar quantity times, which is positive, times x, y, z. Right, but that vector just points straight away from the origin. From the origin to x, y, z. Right, so that looks like that. Right, so if the temperature at any given point is inversely proportional to its distance from the origin, temperature inversely proportional to its distance from the origin. Oh, I'm sorry. That negative, I lost the negative somewhere. Negative 1/2. Yeah, these are negatives. Oh boy. Negative, 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 negative. Negative, 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 negative. Negative, 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 negative here, negative x, negative y. Well, I could leave the negative in there. You know, which points straight from x, y, z to the origin. To 0, 0, 0. Right, so the rate of change of temperature is inversely proportional from the distance to the origin. So the heating isn't from the outside, the heating is from the inside, excuse me. Inversely proportional to the distance from the origin. So as the distance gets greater, the temperature gets lesser. So it's a metal sphere that's somehow heated from the center. So it's hottest at the center. So at any given point, you're going to get hotter as you move towards the origin, if that's where the heat source is. Right. So that's the gradient in that direction there. So this is the point x, y, z inside the sphere or on the sphere. And the gradient points directly at the origin because, you know, the temperature is inversely proportional to the distance from the origin. So the tinier the distance from the origin, the hotter you are. The further the distance from the origin, the cooler you are. So the heat source is at the center. So if you want to get hotter, move straight towards the center. Alrighty. Moving on to section 4.7. Maximum and minimum problems. So first one is number 311. So for the following exercises, find all of the critical points. So the critical points of the function, right? What are they for single variable functions? They are where the derivative is 0 or the function is undefined, or like at a discontinuity or something, or some non-differentiable point. So I mean, with single variable functions, we sometimes deal with these funny points, but with the two variable functions, we're not. We're just gonna stick to these nice and smooth and continuous functions. This is just a polynomial in x and y, and polynomials are the standard for continuous functions. So 311, fxy is equal to 3x minus 2 squared plus y minus 4 squared. Find all critical points. Right, that is, find all points x, y, where fx is fy, where both partial derivatives are 0. In other words, the tangent plane is horizontal. Right? Is horizontal. All right, so you just take those partial derivatives and you set them equal to 0. So in this case, the partial derivative of f with respect to x is just 6x minus 4, or no, sorry, 2 times 3x minus 2 to the first power times 3. And then the derivative of that one is 0. And you set this equal to 0. So this just gives you 6 times 3, 18x minus 12 equals 0. So, I mean, you just solve this one straight away. So that's x equal to 2/3. Right? And partial derivative with respect to y is 2 times y minus 4. Set that equal to 0. So that immediately just gives you y equals 4. So that's the only critical point. So 2/3 and 4 is the only critical point for f of x, y. 314, I think, is the next one. So another, just function. Find the critical points using algebraic techniques or by examining the form of the equation. Verify your results using the partial derivative test. Oh, that discriminant thing? Oh, verify using the partial derivative. Take the partial derivatives and just plug them in. Anyway, so this function here, x squared plus y squared plus 1 square root, partial derivative with respect to x. So this is x squared plus y squared plus 1 to the 1/2 power. So that's 1/2 x squared plus y squared plus 1 to the negative 1/2 times the derivative inside is 2x. All right, so getting this nice, interesting thing that goes on with these square root functions. So this becomes x over square root x squared plus y squared plus 1. And you set that equal to 0, which happens where? When's a fraction 0? When is a fraction 0?
The top is 0?
Yeah, just when the numerator is 0 and the denominator is not. Where the numerator is 0 and the denominator is not. So that's just x equal to 0. Because at 0, x equal to 0, this down here is a positive number. X squared is, x squared plus y squared is bigger than or equal to 0. So, I mean, it could be 0, but you're adding 1 to it. So it's never 0 on the bottom. Partial derivative with respect to y, it's the same. It's the symmetric function here. So when you want to take the partial derivative with respect to the other variable, you just, in a function where you switch the variables and the function doesn't change, the partial derivative with respect to the other variable is just the same as the partial derivative with respect to the first variable, switching the variables again. So down here, nothing changes, exchanging the x and the y, but up top, the x and the y just get switched. So this one, just y equals 0. So that's the only critical point. Okay. 316, 318. So this one will be a little more entertaining, I think. 316, x squared plus y squared plus 2. Now, this is again just a simple 316. That's just a simple, because the partial derivative is 2 for x is 2x plus 2. So that's just x equal to negative 1. Y squared, 2y minus 6, so that's y equal to 3. So again, the solving for partial derivatives equal to 0 is easy again. So 316, just do that one on your own. Let's see if we can't do 318 in the last few minutes. So in 318, for the following exercise, use the second derivative test to classify the critical point to determine whether each critical point is a maximum, minimum, saddle point, or none. None of the above. Or you can't tell. Sometimes you can't tell with that, second derivative test. So here we have fxy is minus x to the third plus 4xy minus 2y squared plus 1. So partial derivative of f with respect to x is minus 3x squared plus 4y. And then these are 0. And you set that equal to 0. And then partial of f with respect to y is, well, that's 0, so that's just 4x minus 4y, and you set that equal to 0. So you have two equations and two unknowns, right? X and y are the unknowns, and I have two equations. So that should be sufficient, well, it could be sufficient to give you solutions, not unique solutions, but to give you well-defined solutions. It might not, but, it might be. So here, this second equation just says 4x minus 4y is 0, just simply says x equals y. So we'll plug this into the first equation. So minus 3x squared plus 4x equals 0. Factor out an x, and I have minus 3x plus 4 equals 0. So I get x is equal to 0, or x is equal to 4/3. So two solutions for x. Okay, and then the y has to be equal to that. Right, x is equal to 0 or 4/3. So the critical points, right, and x is equal to y. So the critical points are 0, 0, and 4/3, 4/3. Now, sometimes when you get two solutions for x, or three solutions for x, or something like that, it's not always that the y's will go along with it. I mean, here we had x equal to y, but if you had x equal to, or you had y equal to the square root of x, or something like that. So like you solved the equation, and you had y equals square root of x, and then you had 0 and negative 4/3. Well, obviously the negative 4/3 won't give you a y. So this time they both worked out, but they don't have to be. In this case they did. Check if, using the second derivative test, if these are relative max, mins, saddle points, or neither. So you have to do the second derivatives now, right? So fx was minus 3x squared plus 4y, and fy was 4x minus 4y. So fyy is 4, or sorry, negative 4. fxy, or fxy is the same as fyx, is equal to 4. And then fxx is equal to minus 6x. Right, so at the given points, well, first of all, this second derivative test gives you this thing called the discriminant, which doesn't always tell you what you want to know, but sometimes it does. Right, so it's this 2 by 2 determinant, so it's fxx times fyy minus fxy squared, because these two things are supposed to be the same. In this case, they are. So we need to plug in the values 0, 0. So at xy equal to 0, 0, well, what is this going to be? fxx is 0. fyy is negative 4. And then fxy is 4. All right, so that is 16. No, negative 16. Right, so that is telling us, which is less than 0, which is telling us that 0, 0 is neither local max nor local min. Right, and then at the other point, so at xy equal to 4/3, 4/3, well, the only thing that changes here, so the only thing that changes here is this becomes, so at 4/3, so negative 2 times 4 is negative 8, 4, 4, negative 4. So this is 32 minus 16, which is positive 16. Right, so 4/3 is a local max. Okay, all right, so it's 8:45. So next time we'll finish up talking about this section, and then we'll do some questions and answers. So come prepared with questions you have, anything here from chapter 4 or whatever else you need to ask about. And after we finish talking about section 4.7, we'll go on to some questions. Okay, and then we'll do some review on Wednesday next week before the exam, and then take the exam. All right. So there's less material this time on the exam. So I'm expecting that folks should do fairly well. Okay. So get into the problems, do the homework, and I'm sure y'all will do fine. Okay. Have a good night, everybody.